A heavy radium nucleus hangs in a void and splits. Internal forces tear the atom apart, sending fragments hurtling in different directions at massive speeds. On a cosmic scale, we see the same behavior. Two massive stars rip through a star field, their mutual gravity pulling them into complex, looping trails that seem to defy a simple path. We are observing both of these events from a stationary, everyday perspective, what physicists call the lab frame. From this vantage point, the motion appears chaotic and almost impossible to predict. To calculate the trajectory of every piece of nuclear debris or every wobble of a star, you would have to track the mass and velocity of every single part. The variables involved make the math incredibly difficult. Physics works by finding the specific perspective where complexity gives way to conservation. It is about identifying the properties that remain constant regardless of how many pieces are moving. To understand a complex system, we have to look past the individual pieces and measure the linear momentum of the entire system as one unified entity. Linear momentum of a particle is the product of its mass and velocity. In larger systems, particles create a tangled web of individual momenta. The total momentum, capital P, is the vector sum of those parts. Treating the cluster as a single point bypasses the internal mess. This point is the center of mass. At this coordinate, the entire system follows a single equation. Total momentum equals total mass times the velocity of this center point. Even if internal pieces are colliding or exploding, the entire system glides forward as if all its mass is concentrated precisely at this predictable center. Newton's second law tells us that the total momentum of a system can only change if a force acts upon it from the outside. The rate of momentum change equals net external force. This distinguishes external forces from internal ones, where parts push each other. Since internal forces occur in equal and opposite pairs, they cancel out. Fxt becomes zero, and momentum remains constant. This is the law of conservation of linear momentum. When external forces are zero, the velocity of the center of mass remains constant. The center of mass is immune to internal noise. Whether a nucleus splits or a star explodes, the system's overall journey remains completely unbroken. Let's return to that radium explosion from our stationary lab perspective. We see fragments flying everywhere. Despite the blast scattering debris, look at the invisible center of mass. It continues moving in a perfectly constant straight line, exactly as it did before the explosion. Now we change our perspective. We shift our mathematical frame of reference to lock onto that moving center of mass. From this center of mass frame, the system's forward motion is effectively canceled out. We are moving right along with the event. In this new frame, the product particles simply fly back to back from a fixed central point, moving with equal and opposite momentum. By shifting our frame, we turn a complex, moving explosion into a stationary and perfectly balanced interaction. We apply this same technique to the binary stars. In the lap frame, their intertwined paths were a confusing mass of loops, but the center of mass between them moves smoothly through the star field like a free particle, completely ignoring their gravitational dance. Shift the camera perspective one final time. Lock the view to that central dot. The erratic loops vanish. In the center of mass frame, the stars are tracing two perfect concentric circles. Understanding linear momentum allows us to separate the motion of the whole from the motion of the parts. It is the key to revealing the simple, consistent geometry that exists at the heart of even the most complex moving systems.